Hello everyone. In this video we will explain a mathematics chapter for the third secondary year, scientific sections GS and LS. The title of the chapter is Complex Numbers. This chapter is divided into two parts. This part is a recall on the basics of the complex numbers. And the main objectives of this part are: identify a complex number and write it in algebraic form, a plus ib, where a and b are two real numbers; perform operations on complex numbers; calculate the conjugate of a complex number and use its properties; and finally, represent geometrically a complex number. Let's begin by recalling the definition of the set of complex numbers C and its properties. By definition, there exists a set of numbers noted by C, which is called the set of complex numbers, having the following properties. The set C contains the set R of real numbers. There exists in C an imaginary number denoted by I, such that I to the power 2 is equal to -1. Any element Z of C can be written in the form Z equal A plus IB, where A and B are two given real numbers. In C, we define the addition and the multiplication following the same rules of calculation in the set of real numbers R. As a new vocabularies, writing the complex number Z in the form A plus IB, where A and B are two real numbers, is called the algebraic form of Z. The real number A is called the real part of Z, and the real number B is called the imaginary part of Z. We denote them by re Z equal to A and mZ equal to B. We will continue with two remarks. If the imaginary part B is equal to 0, we say that Z is a real number. If the real part A is equal to 0 and the imaginary part of Z, which is B, is different from 0, we say that Z is a pure imaginary complex number. Some properties: two complex numbers are equal if and only if they have the same real part and the same imaginary part. A complex number is equal to 0 if and only if its real part and its imaginary part are equal to 0 at the same time. Now we'll recall the conjugate of a complex number. By definition, consider a complex number Z equal A plus IB. We define the conjugate of Z by the complex number noted by Z bar, and it's defined by Z bar equal A minus IB. That means Z bar have the same real part of Z, but an opposite imaginary part. Now we will state some properties of the conjugate of a complex number. Consider two complex numbers Z and Z prime and a natural number n different from 0. The conjugate of a complex number is equal to the complex number itself. That means Z bar is equal to Z. Z plus Z prime bar equal to Z bar plus Z prime bar. Z times Z prime bar equal to Z bar plus Z prime bar. Z to the power n bar, it's equal to Z bar to the power n. 1 over Z bar equal to 1 over Z bar when Z different from 0, and Z over Z prime bar equal to Z bar over Z prime bar when Z prime is different from 0. Some properties also: Z is a real number if and only if Z equal to Z bar. Z is a pure imaginary, and it must be different from 0 if and only if z equal to minus z bar. If z equal a plus ib, then z bar equal a squared plus b squared. The most important application on the conjugate of the complex number is how to determine the algebraic form of the quotient of two complex numbers. Consider two complex numbers z equal a plus ib and z prime equal a prime plus ib prime, where z prime is different from 0. That means a prime different from 0 and b prime different from 0. To determine the algebraic form of the quotient z over z prime, we multiply and we divide by the conjugate of z prime in order to obtain a real denominator. Then we take I in common in order to obtain a quantity in the form of a real number which represent the real part of z over z prime plus I, and multiplied by a second real number which is the imaginary part of z over z prime. Now we'll recall the geometric representation of a complex number. We refer the complex plane to a direct orthonormal system OUV. By definition, if a and b are two real numbers, to each complex number z equal a plus ib, we associate a unique point M of coordinates AB and a vector W of coordinates AB also, as shown in the figure, where A is the abscissa of the point M and B is the ordinate of M. M is called the image of the complex number Z. Also, to each point M of coordinates AB and to any vector W of coordinates AB also, we associate a unique complex number Z equal A plus IB. We say that Z is the affix of the point M and the affix of the vector W of coordinates AB. As a representation, we can write M of affix Z and omega of affix Z also. Remark, the points M and M prime of respective affixes Z, which is equal to A plus IB, and Z bar, which is equal to A minus IB, are symmetric with respect to the real axis or the abscissa axis. Now we will state some properties on the geometric representation of a complex number. Given 2 points M and N of respective affixes Zm and Zn, and 2 vectors W and W prime of respective affixes Z and Z prime. As shown in the figure to the right, this is the point M, this is N, this is the vector W, and this is the vector W prime. The first property is the vector W plus W prime has an affix equal to Z plus Z prime. Geometrically, this is diagonal of the parallelogram constructed by the sides that are W and W prime. The second property, the vector KW, where K is a real number different from 0, has an affix equal to KZ, as shown on the figure. The vector Mn has an affix equal to Zn minus Zm. The midpoint I of the segment Mn has an affix Zi is equal to Zm plus Zn over 2. Now we will solve some application exercises. We want to determine the algebraic form of each of the following complex numbers. Part A, Z equal 1 minus I to the power 4. We write Z in the form 1 minus I squared to the power 2. We expand 1 minus I to the power 2, which is equal to 1 minus 2I, plus I squared, which is equal to minus 1, and here we associate the power 2 to minus 2 and to I to obtain the final result, which is equal to minus 4. Part B, same question, the algebraic form of the quotient 1 plus I over 1 minus I. We multiply and divide by the conjugate of the denominator, which is equal to 1 minus I. That is 1 plus I. We multiply and divide by 1 plus I. 1 plus I into 1 plus I, it's equal to 1 plus I squared. 1 minus I times 1 plus I, it's equal to 1 minus I squared. I squared is equal to minus 1. Then the denominator will be 1 plus 1. So 1 plus I squared equal 1 plus 2I plus I squared, which is equal to minus 1 over 2. 1 minus 1, 0. We obtain 2I over 2, which is equal to I. Try to solve this part on your own to obtain the following answer. We should multiply by the conjugate of the denominator, which is equal to x plus 3 minus 2I. We multiply the numerator and the denominator. Now we are going to solve an important exercise. In each of the following cases, we must determine the set of points M with affix z equal to x plus iy, where x and y are real numbers, satisfying the given condition. First part, the quotient z minus I over z plus I is pure imaginary. First, we replace z by x plus iy. Second, we multiply and divide by the conjugate of the denominator to obtain the algebraic form of the quotient z minus I over z plus I, which is x squared plus y squared minus 1 over x squared plus y plus 1 squared plus I into minus 2x over x squared plus y plus 1 squared, in condition that z plus I different from 0, then z different from minus I, and that is x different from 0 and y different from minus 1. The quotient is pure imaginary if its real part is equal to 0. Then when the numerator x squared plus y squared minus 1 is equal to 0, and at the same time we must have x different from 0. The equation x squared plus y squared minus 1 equals 0 is the circle of center O and radius 1. Then the set of points M is this circle of center O and radius 1, deprived from the points of intersection with the ordinate axis or the y-axis, which are the points of coordinates 0, 1 and 0, minus 1. Now we will observe the motion of the point M satisfying the condition that z minus I over z plus I is a pure imaginary. Watch as z1 moves on the x-axis, then M moves on the circle of center O and of radius 1. Now the second part of this question, we want to find the set of points M of affix z such that the quotient iz minus 2 over z plus 3 is a real number. We begin by replacing z by x plus iy and by multiplying the numerator and the denominator by the conjugate of the denominator in order to obtain the algebraic form of the quotient, satisfying that x must be different from minus 3 and y different from 0. The quotient iz minus 2 over z plus 3 is a real number if its imaginary part is equal to 0, such that x different from minus 3 and y different from 0. We then obtain x squared plus y squared plus 3x plus 2y is equal to 0, which is an equivalent equation to x plus 3 over 2 squared plus y plus 1 squared equal 13 over 4. This equation represents the set of points M, which is the circle of center of coordinates minus 3 over 2 minus 1, and having radical 13 over 2 as a radius, deprived from the point minus 3, 0, which is the condition x different from minus 3. And finally, we will meet again in the second part of this chapter, the trigonometric form and the exponential form of a complex number. Good work and stay safe.